Thank you for joining me for the last part of our chapter 1.3 regarding crystal structure determination. And of course, the course is a solid state physics. So here, what we will do first is that we will continue our description of the Laue theory, and then we will derive the Laue condition and elucidate a little bit how the basis of the lattice can then be characterized when we perform X-ray diffraction experiments. And this was one of the differences that we discovered takes place between the Bragg theory, which is a simplistic theory to understand X-ray diffraction, and then the Laue description. And after that, we will introduce to you the Ewald's construction and Ewald's sphere. What are those concepts that allow us to understand that what specific scattering vector values we are then seeing diffraction peaks and how they relate to the reciprocal vector values, G's, and how they then relate thus to the Miller indices associated with a given periodic structure. And finally, in the final part, we will go through briefly and mention, discuss other methods that can be used to determine different periodic structures. So that's what we will be covering in this final part of the lecture, and that's what we will then proceed in doing. So we will return to the original X-ray diffraction problem, and we discovered previously that the intensity irradiance that we're actually measuring into a direction of K prime, that's the scattering direction as shown in the figure on the right hand side, that was proportional to the modular square of an integral over the volume of the whole sample, and we are integrating over the electron density rho r, and then we have the exponent minus I kr, where k is the scattering vector, and this is what we're integrating, and we take the modular square because it's irradiances we're actually measuring. We can place in what we discovered, what is the how we can describe electron density also as a Fourier series. So that's what we are inserting next into the equation, that we have the modular squared, and now we are changing rho into the Fourier series description. So we sum over the reciprocal vectors, so these n prime, m prime, and o prime. So we're summing over G, and we have the Fourier coefficients rho G, and then we are integrating exponent exponent I G minus K, and that's what we are left to integrate over. And this is the modular square we're taking here. And please note what we have like mathematically inside the integral here. The integral, this is just a plane wave, and we are integrating over a quite large volume out of that. So we are left with an oscillatory integral, and this is actually a known integral from previous courses already, and this can be solved to be a V, the volume over which we are integrating, times the delta function of G minus K. And with that, we can actually simplify our description of the irradiance that we are measuring in a given direction of K prime. So it's the modular square of a summation over G's times the Fourier coefficient of the electron density rho times V times delta function G minus K. And basically we see that this delta function G minus K is just picking out a specific G values that equal to the capital K, the scattering vector. So that is what we are then left. So we are left something, the irradiance we are measuring in a given direction is then proportional to the volume out of which we're getting the signal times the Fourier coefficient rho K of our electron density. And now we see that actually, like in fact, there's like a physical interpretation of that diffraction peak already taking place, because we are now like seeing actually like a contribution only of a given Fourier coefficient in our signal that we are measuring. So like I said, the Dirac delta function delta there picks out a specific reciprocal lattice vector G, and this happens when Laue condition is being fulfilled. So when this capital K, the scattering vector, which was equal to K prime minus K, that equals to a very specific reciprocal lattice vector G. And this is known as a Laue condition. And now we see that depending on what is our crystalline structure, so that what are the reciprocal lattice vectors that also define it. So it's just a matter of description. Do we use the normal space description of a lattice, or do we use the reciprocal lattice description? Basically, they are just like a Fourier pairs of each other. And we see that this must be equal to k, and this specific condition then gives us a scattering peak. And please note on the kind of terminology or mathematical notation we're using here. Like, please remember that we are in experiments. We are maybe controlling the direction of the incident Röntgen rays, so k, and we may also detect the scattered Röntgen rays in a different direction, X-rays, so k prime. So the scattering vector capital K is actually their difference. And in experiments, in principle, we can we can adjust either of these when we are performing experiments. And that's how we can scan over different values. And then this I guess maybe one could, instead of just saying k prime here, one could use k prime and k, so that in fact this measured intensity is in fact a function of two variables. That's what I want to say. So instead of a single variable, it might be more appropriate maybe to just explicitly tell to you guys that this is actually a two variable function. But nevertheless, that's still our condition, and we will now progress forward. So we see diffraction peaks, and we see them at a very specific k values, and they correspond to the different reciprocal lattice vectors that we may have. So now we basically have is that we have means to measure these charge density coefficients, rho g's. The trouble is that when we are measuring the modulo square, and these coefficients in real life, they actually are complex valued, and this is an issue because we can only directly measure the amplitude because we are measuring the modulo square, and we don't have the information of the phase term phi g if we describe the rho g coefficient using a complex notation where we have the modulus, we have the amplitude of the complex number plus exponent I phi, where phi is the phase. And this is the information we don't have right now, like what is this phase term. And this is actually important because we need to be able to extract the actual real valued rho after the experiments. And interestingly enough, at least I like mathematics a lot, is that this kind of problem, if you want to describe it in more general terms, is that it's known as a phase problem. So you can go into Wikipedia and you can have a look and knock yourself out that these kind of phase problems actually arise in many different branches of physics and in many engineering topics. So this is not the first time humankind encounters this kind of phase problem, not by far, not that. So this is a very generic type of a problem engineers and physicists are solving. And in X-ray diffraction, the de facto tool how this phase problem is being solved is that we are iteratively solving. And so basically we are comparing measured diffraction patterns, and we are measuring these irradiance patterns, and we are comparing them against some predicted patterns based on for example, the math we have just discovered. And we are iteratively improving the agreement between the prediction and between the actual measurements. And we are iteratively, with this kind of method, we are kind of trying to find out the kind of possible solution that provides us the measured diffraction profile, diffraction pattern. And once we are now there, then usually it's relatively unique solution, but that is not always the case. So there is a little bit of ambiguity or a possibility for ambiguity when we are solving phase problems. It's not always granted that the way how do you solve and the way how do you find a solution, that the solution is actually the unique solution, but it might actually be just a single solution out of a set of many. So that's the trouble that we are facing here. And what we do next, like I promised, is that we want to relate these Fourier coefficients to the basis of the lattice, because then hopefully we can appreciate that X-ray diffraction is quite a powerful technique, because it provides us information not only on the position of the lattice points, but also what's inside the lattice point. So what is the basis of the lattice? And for clarity of description, we only consider scattering amplitude E, G here, and not the irradiance. And in this case, we just can simplify the notation. But I hope you appreciate the difference that in real lives, like we would be measuring like the irradiances. So like the treatment should be generalized a little bit, but we don't do it here. We don't do it here for conceptual clarity. So okay, our scattering amplitude calligraphic E, which is a function of G, we assume that that's proportional to the V times rho G, and this is what we discovered earlier, right? Remember, just previous slides. This is the proportionality we found out. And now we can perform an inverse Fourier transform, and this will give us the Fourier coefficient rho G. And when we place that into our proportionality we see above, we get a condition that the scattered field is proportional to this term V times rho G, and now we place inside of the rho G the definition of how do we calculate the Fourier coefficient, and we are left with V divided by 1 over V cell. So we are integrating over the unit cell of our structure, and then we have in the integrand, we have the rho, our electron density, times exponent minus I times G, the reciprocal lattice vector times R. And we are integrating over volume here, dV. And we can simplify the notation. We can define that the V divided by V cell is capital N. And then we are left with an integral of the given form. And this integral that we are left with, that we are performing over the unit cell, this is actually known as a structure factor. So this integral, we can like redefine it to be Sg, and this Sg term is known as a structure factor that is being used. And this is something that will provide information of the basis of the lattice. Next, what we do is that we assume that the contribution of valence electrons to the overall measured diffraction profile is very small. It's negligible. And this is an okay assumption to make when we are not dealing with very light elements, and this is what we will do here. And this means then that only the electrons nearby the nuclei, so these so-called core electrons, so not the valence electrons, but only the core electrons, are relevant. And this is a pretty valid approximation to make in practice when you're not dealing with the lightest of elements. And with this help, with this assumption, we can then write the whole electron density rho as a sum of individual densities of atoms that may be inside our basis of the lattice. So the electron density then could be written as a form of summing over I, dummy index I, and we have different contributions of different atoms. So in essence, this rho I in a position of R minus Ri is an electron density corresponding to the ith atom that we have in the basis of the lattice. And with this way of writing the charge density rho, the electron density, the structure factor Sg now becomes Sg equals a sum over these i's, the number of atoms we have in the basis of lattice, E exponent IgRi, and we are integrating left with an integral over the atomic volume rho I over R prime times E minus IgR prime. And now we can redefine this leftover integral, and we can simplify the summation, the notation slightly easier. So we're summing over indices I, and we have exponent IgRi times Fi, where this is Fi is known as a atomic form factor. So R prime is R minus Ri, simplify notation, and the integral Fi is known as the atomic form factor. So this is what we have in our notation now. and this form of the structure factor is G. This is what we have discovered, that this is the form we can write. And this is known as the structure factor of the basis. And what it tells us is that this shows that we can actually extract information even of the basis of the lattice when we perform X-ray diffraction experiments. And this is mind-boggling of a result, because this is the tool that allows us to understand how crystalline materials are being formed, what's their structure, and also in a more modern days of science, like it also allows us to characterize quite complicated biological molecules, proteins, structures, and that's the kind of main tool where X-ray diffraction is nowadays being utilized. So basically, the figure I'm showing you, I was ripping it off from Wikipedia, and thanks for Jeff Dahl for making it and putting it there. This shows an actual measured X-ray diffraction pattern, and it's been measured out of a crystallized enzyme. So the challenge in X-ray diffraction experiments and in trying to understand 3D configurations of proteins and enzymes and different structures, that how can one make small crystals out of them so that one could make X-ray diffraction experiments. So it's a single enzyme is not enough in practice to material to be used to characterize the structure. And that's why one must make a crystal out of the structure first and then perform X-ray experiments. And this is the challenge often that the people are facing. But once you're able to crystallize your structure, your molecule, your protein of interest, then you can easily do X-ray diffraction experiments, and then you can extract the structure. And this pattern that shows here shows that there are some different peaks, and those different peaks correspond to these different reciprocal vector values G's, and then is related to this structure factor of the basis. And these relative strengths in each of these spots allows to determine what is the structure of the enzyme. And this is the kind of like a end result that we have on this part. So we can do X-ray diffraction experiments, and we can in fact even get information of the basis of the lattice. So I will now stop this part of the lecture, and I will hurry forward for the Ewald construction. And this is hopefully a neat graphical trick that helps you to understand when we have those diffraction peaks emerging. And what we discovered earlier is that we saw that the scattered X-ray field is of the form, and now for simplicity I'm just describing with fields, I'm not using irradiances, and we saw that it was proportional to the volume of the crystal times the rho G terms, and this was found to be in a form that we had this N or V times V cell, and then we were integrating over the charge density times E times minus IGR over the volume, and we know that the charge density, it's electron density, not just charge density, because we are not integrating over atoms, ions, we're just integrating over electrons. So rho, the electron density, was the lattice periodic electron density we want to figure out. Mathematically, of course, what we see, this above integral, is really a Fourier transform, and that's what we're mathematically doing. And that's also what the reciprocal space is in practice. It's our description of a function in the Fourier domain. And maybe that helps you to understand what is reciprocal lattice and reciprocal space. So physically, because we have a lattice periodic function, we need that only certain spatial frequencies, if we would make a Fourier transform, like only certain spatial frequencies exist. And these arise from the fact that we have a lattice periodic function. Like atoms are only in very specific locations, and subsequently the electrons are also in a very specific place in the lattice. And that gives rise to the fact that the X-ray diffraction pattern like only has specific peaks in given locations. And next we will study a little bit how this effect happens and how we can graphically understand like when these conditions are being fulfilled. And we start by just noting that the Bragg theory that we treated early on, like it's really just a special case of this more general Laue description we have now formulated. And please also note that this reciprocal vector G equals to k prime minus k, and that was the scattering vector. This is actually a vector relation we are seeing here. So these are vectors. Please keep this also in mind. And either way, like we can either just use vector algebra to understand things, or we could also separate this condition into components, and then we would actually have several conditions. And if I recall correctly, if you go to Wikipedia and then you seek what's a Laue description or what's a Ewald construction, construction, I don't remember where you end up, but in Wikipedia, usually this condition is being separated into its components. But it's the same condition, same treatment, but it just looks slightly different because it's not being utilizing the vector algebra, rather scalars. And for simplicity here, what we are doing is that we are restricting ourselves to a specular reflection. So basically, like we only think that the incidence angle and the reflected angle, they are the same. And we also, for simplicity, we restrict to the case that we're only dealing the single plane of incidence and that the scattering vector remains in that plane of incidence. So these are simplifications, and of course in real X-ray diffraction experiments, this is not the case, but this helps our treatment right now, because this is a little bit complicated to grasp in full 3D case. So we have the Laue condition, capital G equals k prime minus k, and we can really graphically illustrate what this condition means. And how we can do so is that we can take use of a so-called Ewald construction. And this is a picture that hopefully highlights what happens in this procedure and how do we make this Ewald construction. So first, what we do is that we draw the k, the incident vector, incident plane waves direction, and we just end this k into some of the reciprocal lattice points. So what we do here is that we just start and we draw and we just make sure that we end up in one of the reciprocal lattice points, and that's it. This is the first stage. And the second stage or step in our procedure is that now we draw a circle that has a radius, of course, of this k, and we center this circle at the origin of k. And that's had been drawn in the figure already. And then the third step is that now we have Laue condition. So G equals k prime minus k. It's being fulfilled at those points of the circle that they intersect the reciprocal lattice point. So when this circle intersects some point, we can draw a G vector here, because by definition, we can, like this reciprocal space, like we can move from any lattice point to any other by just multiplying with a proper G. So then by definition, whenever like we have a circle and then it crosses one of these reciprocal points, we know that the Laue condition is being fulfilled. And this is the way to understand what happens, or maybe it helps for you to understand. Another way is just to physically think what G corresponds to, so that if you understand that you can relate that to the Miller indices and to a specific plane, then you see that you can relate the measured peak to the G and thus to the given specific planes. And we can easily extend this construction to three-dimensional lattices, at least conceptually, maybe not in practice. but at least like conceptually, it's quite straightforward. Basically, we just either can consider an Ewald sphere. So instead of drawing a circle, we would make a sphere into a three-dimensional space. And then we would have like, instead of a plane of reciprocal lattice points, we would have a 3D configuration of them. Or another way of thinking it is that we would construct different lattice planes sequentially. So we would just draw things one plane at a time, and then we could actually do the construction. And what we see, in fact, by just drawing these figures, is that in fact this Laue condition is not very easily met in practice. It's not often the case that this circle is actually being intersecting a reciprocal lattice point. And what this means that it's very unlikely that this condition is simultaneously met for many points. And what this physically means that then when we see a single diffraction peak, usually it only corresponds to diffraction associated with a very specific g-vector. And this physically means that we can uniquely relate that specific diffraction peak to a specific Miller indices, and thus to a specific plane in the crystalline structure. So this is what we can do in practice, because it happens to be the case that this condition is not very easily met. And now we can also just verify, like what we discovered using the Bragg theory, that we can very easily verify the upper limit for the wavelengths of interest when we are shining X-rays into our sample. And then we can see that the circle of radius is the amplitude of k. And this needs to be long enough, this circle of radius, that this condition can be fulfilled at all. So basically the 2k, which is equal to 2 times 2 pi over lambda, that's the definition of k. And this must be longer than a modulus of a reciprocal lattice vector. And this equals to 2 pi times a in the 1D case, and this gives us the condition that the wavelength of my X-ray must be smaller than 2 times a. And this is exactly the same limit that we were estimating using the simpler Bragg theory. So this is a kind of like good sanity check to verify that indeed this more general treatment also provides the same predictions as the simple one. And it's good to see that, okay, like indeed we do get reasonable predictions out of the more general case. And now that we have covered the basics of Ewald construction though, we are pretty much ready to kind of move to the final part, where we are just very briefly discussing what other techniques there are that can be also used to characterize crystalline structures. So then to the final part of other methods regarding structure determination, and what we can do in addition of X-rays, we can also make electron or neutron diffraction experiments, and that's of course possible. The advantages of this approach, well, for example, we have strong interactions, so electrons scattering out of electrons, or that's quite easy to see, like a scattering event happening. Electrons, they are quite abundant. They can easily be generated, and even more so, they can easily steered, because like it's a charged particle, and then with static electric and magnetic fields, we can easily steer electrons, and we can give them a given amount of energy. So that works with electrons. With neutrons, it's not that easy, because neutrons are not charged particles at all. So then it's actually like very difficult to try to guide neutrons. Instead, you actually don't guide. You just have a neutron source that is powerful enough that you have a lot of neutrons, and then you just try to collimate your neutron beam, and then you place your sample accordingly. But you don't really guide neutron beams yourself as such. And this is in comparison, like with X-ray optics or X-ray diffraction experiments. It's not that easy to kind of focus and guide X-rays into different locations. So with electrons, it's quite easy to control the flow of electrons, that they can be easily steered, but X-rays, it's not that easy to steer, and neither that is the case for neutrons. The possible advantages and actually practical advantages that we get is that now we are dealing with matter, real particles, and they are fermions, electrons and neutrons, and that means that they also carry magnetic moments. And what this means in practice is that it can be used to probe magnetic ordering. And this is a real benefit when we are using especially neutrons, because it can provide us a means to understand domain formation of magnetic domains. And for example, we can distinguish between different magnetic ordering. So ferromagnetic ordering versus this anti-ferromagnetic ordering. So that these kind of different orderings can be studied by performing experiments with fermions, because they have spin, magnetic moments. And of course, there's a possibility to perform kind of hybrid techniques, so electro-optical or optoelectronic imaging, and that allows further sophistication to make experiments. I would here say that when you would want to understand lattice vibrations, then pretty quickly you end up using these kind of tools. So that if you want to understand what kind of phonons you may have in your system, then you may need to resort to these kind of hybrid techniques, because you will probably need to be able to measure some energy differences that takes place in the scattering experiments, and then usually the easiest is that you also have some photons plus some electrons involved in the processes. Then something about the disadvantages. Sometimes strong interaction is not an advantage anymore, but it's actually a disadvantage. And when that happens, is that it may be the case that the kinematic approximation. So we started with this, if you recall, and we were saying that the X-rays just scatter once from our sample, and that's it. That's the interaction that we have. But when we have very strong interaction, it may be the case that we actually have multiple scattering processes, and then they obscure what happens in these scattering events. And this may happen when we have a very strong interaction, and sometimes that's a disadvantage. And when we are dealing with low energy electrons, the downside of them is that they don't penetrate very deep. So mostly they're applicable only to surfaces and interface studies. And that's also a bummer, because that's not always the case that we want to study. And then there's also a possibility for inelastic X-ray scattering. And I would say that this is this kind of hybrid electro-optical imaging technique, because how do you then measure the energy difference? That it might be easier that you actually come with electrons and then you measure some photon being emitted, or vice versa. But in any case, there's also a possibility that you may make X-ray scattering, but now instead of elastic scattering processes where energy is being conserved, some of the energy is being absorbed into the lattice that you study, and this makes the scattering process inelastic, and the creatures of that they absorb the energy are then lattice vibrations in practice. So that the phonons are being excited, and with these kind of experiments, you can, for example, extract experimentally the phonon dispersion relation, but more of that and its importance later on when we are starting to treat thermal properties of lattices. So these are the kind of main things that come to mind when we are speaking of these other techniques. That many of them exist, and they have their advantages and disadvantages, and it's not always easy to choose the best technique, and not all the techniques are most suitable for all the studies. So you need to kind of know what are the smart tools and techniques to use when you make experiments and then you study some systems. I had something in the early part regarding electron and neutron diffraction, but I have forgotten it. But maybe it's not that important in the end. So I think I will stop here. So this is now the end of our first lecture. So we have now covered crystal structures, and we have started our journey on the solid state physics. And hopefully now you start appreciating the fact that indeed it is the periodicity of our solid that matters a lot. And we have already seen that it matters great deal when we are performing X-ray diffractions. So when we are characterizing these structures, and later on the same trend will continue. So in the next chapter, which focuses on bonding of solids, we are now then trying to understand what are the kind of microscopic origins of these different structures. So what gives rise to different structures? And then once we have gone through that, we will then slightly, in small steps, extend our approach to more and more complicated things. But thanks for following up, and please continue with me to the upcoming lectures. So thanks and bye-bye.